Hi folks, this presentation is going to be based on section 2.1 of the textbook. So today I'm going to review an idea from a previous presentation and also talk in more depth about the tangent and the velocity problems. So I mentioned earlier two fundamental problems in calculus. So one of them is finding the slope of the tangent line to a curve passing through a point P. We considered a different point Q in the curve and then we approximated to the original point. We also saw that when we have complicated regions, we can approximate its area by the areas of rectangles, as we have in the second picture in the slide. And you may be wondering, what do these problems have in common? So in both cases, we use approximations to obtain the answer that we want. Also, when we were studying the tangent problem, we used the notions of tangent and secant lines. The word tangent derives from Latin and it means touching. If we have a circle, as in the picture on the left, then the tangent line is going to touch the circle at only one point. But it may be the case that the tangent is going to touch a curve in more than one point, as we have in the picture on the right. I said previously that a tangent touches a curve in only one point, but that was not a precise definition. This is only a good definition if we're talking about circles. The word secant comes from the Latin word secans, and it means cutting. In this case, the secants are always going to cut a curve in more than one point. So we talked generically about the slope of the tangent line, but let's take a look at a concrete example. So let's find the equation to the tangent line to the curve y equals x squared at the point P11. So the equation of a line is given by the expression in the slide, y minus y0 equals m times x minus x0, where x0, y0 is a point in the line and m is the slope of the line. So we already have the point 1, 1. All that we need to find is the slope of the tangent line. We know how to graph quadratic functions. So this is the graph of the given function y equals x squared. And then in this case, we're going to have a parabola that is concave up and the vertex is in the origin. So how can we solve this problem? So far, we only know one method. That's the method that we're going to use. We're going to obtain a point Q in the curve, and then we're going to move it along the curve closer to P. Well, if the point Q is a generic point in the curve, then it has to have the form x squared because it has to satisfy the equation of the curve. Since P is the point 1, 1, then we know how to evaluate slopes of lines. So the slope of the secant line that passes through the points P and Q is going to be given by x squared minus 1 over x minus 1. And then we are going to denote this slope by m sub pq, as we have in the slide. In this slide, we have two tables with the slope of the secant line PQ for different values of x for values that are close to 1. So on the left table, we have x values that are bigger than 1, and on the right table, we have x values that are less than 1. And something common between those two tables is that as x gets close to 1, what happens to the slope is that it's approaching 2. It's getting very, very close to 2. So at this point in our course, the values from those two tables are the best tools that we have to evaluate limits. And we're going to say that the slope of the tangent line, which we are denoting by m, is going to be the limit of the slopes of the secant lines as Q approaches P. This Q arrow P in this equation means that Q is approaching P. And so I want you to notice that when Q approaches P, the first coordinate of Q is going to be close to 1. And because of that, we have in the second equation in the slide, x arrow 1. That's what it means. And then the fraction that we have is simply the definition for the secant line m sub pq, the slope of the secant line m sub pq. So for now, we're going to simply assume that our conclusion from the two tables is correct. And then to answer the original question, we simply plug m equals 2 and x0, y0 equals 1, 1 in the equation of the line. So the first equation that we have at the bottom of the slide is called the point slope form, and it's one of the correct solutions. But we can also manipulate this equation to get the second one, which is also correct. Now let's talk about the velocity problem. We're going to divide this topic in two parts. The first one is the average velocity, and the second one is the instantaneous velocity. Well, let's start by talking about something that I really like, which is traveling. Let's suppose that you want to go from Rio to New York, and then you want to have an idea of the speed of the airplane. So we can find this information on the internet that the distance between Rio and New York is approximately 7,754 kilometers. And then a straight flight from Rio to New York lasts about 12 hours. So you know that the velocity is measured in kilometers per hour, so it just makes sense that the average velocity is going to be the ratio between the distance and the time. So the average velocity of the airplane is going to be approximately 646 kilometers per hour. So we represent the situation symbolically by the expression that we have at the bottom of the slide. So we say that the average velocity is the variation of position over time. And then we also represent this by delta S over delta T. And I want to point out that delta in our context usually means variation. Now let's move to the discussion of the instantaneous velocity. Galileo, the scientist in the top picture, he did an experiment at the Tower of Pisa, which is in the picture below. What he did was he dropped two objects of different masses, and then he discovered that the time that it takes for the objects to get to the bottom doesn't depend on their masses, which is, I would say, counterintuitive, because if we were to guess that one of the objects is going to get to the ground first, we would think that the heavier object would reach the ground first. But actually, what he discovered is that it doesn't depend on their masses. And then if we neglect air resistance, it's going to depend on the square of the time that the object is falling, as it says in the slide. And then we represent this fact by this function that we have in the slide, s of t equals 4.9 times t squared, where s is the distance in meters fallen by the object after t seconds. So let's pretend now that we are in Italy and that we drop an object from the top of the Tower of Pisa. And then we want to know what is the instantaneous velocity at 5 seconds, for example. So from the travel example, and probably also from your own life experience, you know that the average velocity is given by delta S over delta T. And then if we evaluate the average velocity over a very small interval that starts at t equals 5 seconds, well, we may think that this should give us a good approximation to the instantaneous velocity at t equals 5 seconds. So we have this table where we have some approximations, and then you can observe that the best approximation is going to be in the last line because the time interval is just 0.001 second. So it seems that the instantaneous velocity is going to be 49 meters per second. So now let's analyze this problem from a different perspective and also from a more generic perspective. We know that the distance as a function of the time is given by s of t equals 4.9 times t squared, which is written in both graphs. And we also know that this function is the graph of a parabola. And also, we know the formula for the average velocity. Now, if we consider 2 points P and Q, where P has x coordinate equal to A and Q has x coordinate equals to A plus H, the average velocity is going to be given by the expression that we have in the slide, which can be simplified to S of A plus H minus S of A over H. The idea of the table in the previous slide is pushing the process of evaluating the average velocity to the limit. This means that we will approach Q to P, and when it happens, H will go to 0, as I'm going to show you in a GIF. But actually, before I show you the GIF, I want to mention that the curve in the GIF is not related with the curve for our problem, but the idea of H going to 0 is the same. So the instantaneous velocity at A is given by the limit of S of A plus H minus S of A over H as H tends to 0. So the average velocity problem is going to require us to evaluate the slope of secants, and the instantaneous velocity problem is going to require us to evaluate the slope of a tangent. That's it for today. So as usual, don't forget to smash the like button and subscribe. See you next time.